Everyone, welcome again. In the last video we saw how a tweak is installed and also what's the structure. In this video I'm gonna go on and see how we can reverse engineer a part of this tweak. This is a very interesting tweak. It's says global jailbreak detection bypass. It's a very effective one. It patches a lot of system stuff, and as you can see, some of its functionalities that here in this screenshot I have. It says, for example, it patches system calls, and in this video you're gonna see that how to reverse engineer or how it really works. And there's an interesting vulnerability or weakness in the logic of how this patch works. So what I'm gonna do, I'm gonna load this file which we have. I already downloaded, and in the previous video you can see how to download this file. I already downloaded, extracted it, and then we have this binary file lib. So it is a Mako file. It's a binary, it's dynamic library. One thing we can do with this one is that if you issue the file command on this one, you're gonna see more information about this. So if I write file dylib, you see it's a fat Mako file, and it has 2 slices, and I'm gonna focus on the ARM61. I'm gonna load it and see how it works, how you're gonna find the desired part, and how to exploit that thing. So what's the end goal here? What this, as I already said, what this tweak does is it hides if the application is jailbroken. So if you have an application, a banking, a gaming application which tries to check if the device is jailbroken or not, it's gonna hide that one. By that I mean what? Well, here I have a few path that on different jailbreaks you'll have different path. In a regular iOS device you'll not have, for example, this you'll not have this path in a regular iOS device, but when you jailbreak your device, there are chances of, well, depending on the jailbreak type, you're gonna have these paths. So if a game wants to detect if an iOS device is jailbroken, may try, among many other stuff, may try to see if it can delete, or let's say they may try to find the existence of these paths through different methods and system calls. Maybe list its permissions, so that says, oh yeah, there's a file, or try to delete some file there, or try to create a file there. So many other ways to do. What this tweak tries to accomplish by patching the system calls is that it tries to prevent the application who tries to access these particular paths from accessing it and gonna show it to the application that either this path doesn't exist or something. So also if you're following, just don't forget to click here and enable this tweak for the apps of your target, which I already did. So let's go on. I'm gonna launch Ghidra. I already loaded, worked something. Okay, so I already loaded it. I'm gonna click on my project. Cool. So I can maybe pull this up here. So when you load, of course you'll not have this compiled code. The code that you will see will be, I don't know, maybe something, like this. Usually you'll not have undefined functions without name. You can rename functions. You can do much more, but that would be a video specifically focused on Ghidra. So when you load it, you'll have something like this, and you'll look at this and say, okay, what do I do with this? First thing that you may want to go and see, well, what external symbols does this binary depends on? And the reason for that is, even if this binary does a lot of obfuscation, if it's using something external, it needs to have the same name and doesn't like change it, because, well, how can I detect the loader that what external symbol functions, let's say, it depends on? Since it's a iOS Apple related ecosystem binary, you'll have a lot of these NS or other symbols that betrays that, yeah, this is a Objective-C binary. So if you go and scroll down, you're gonna see some symbols that seems familiar. For example, change directory, or to root, connect, create, and fork, and a lot of them. Get stats, file system stats. The one that's interesting for in this case here is, let's scroll down to find it. Yeah, the unlink one. So the unlink system call, in simple words, you can think of it, the unlink, as a delete something. So that would be the very rudimentary and easy, simple thing to say. So from here, we can see that this been cross-referenced at least in 2 other places as the Ghidra analyzer found. One here, if you just hover it, you'll see it, and another in this location in address 8F6C. You can double click and you'll be brought there. So of course I work on this and I have some functions renamed, but you can see that if you don't work on it, and you see it like this. So something is loaded in a register, a function is called BL, and then something is loaded in a register, and that sort of stuff. So of course I worked on this, and what I found here, that load register 0 with a pointer to the unlink symbol, and then also address of another function. It was named something like this, but I named it, just said, okay, maybe it's another function which replaces the link to another register. And then in the last register, there is a another pointer loaded, which I named it again pointer to the original unlink, and there is an also UI. And then it branches to a function called mobile substrate hook function. It's a very interesting function. If you copy this and go to just search it, it's a part of the Cydia now mobile substrate, and it takes 3 arguments: a symbol, a hook, and alt. So it says the address of code to instrument with replacement code, the address of an ABI compatible replacement for the code, a pointer to a function pointer that will be filled with a stub, which may be used to call the original implementation. This call can be null if you do not proceed to the original. So what happens here is you basically replace, back to Ghidra, you basically here, the author replace the original unlink with its own implementation and pass the call to the original unlink, just in case he needs it. And then the mobile substrate hook function is called. So what happens is if an application tries to delete a file, since this will be loaded, this library will be loaded into the space of the application. Any application that it's enabled for. This will be loaded to that space, and then when the application tries to delete something and tries to call this function, basically mobile substrate, CDS substrate, will stop calling this function. This function will be called, and if needed, the myLink function will be provided with the original pointer. So hooking a function. Cool. Let's see what's inside the myUnlink function. If you double click on this one, you see this code. There are a lot of cases that you'll see a bunch of no-op operations here. And then in another cases, you'll have an address loaded, and then you click on that address, and then there's another address. So it's like sort of just a data in an address, like indirect calls, let's say. So if you try to see this, you'll not be, even your decompiler will not be able to have the full picture of what's happening. So you need to work on it. You need to identify the local arguments. You need to identify like inline a lot of branching, as it happens, like branching here. You have to inline it, which I already did inline these because it will take some time to do it on the stream. And if you look at the decompiled code, it kind of resembles C code, which in fact this Objective-C, since we have Objective-C message send, Objective-C retain, so this Objective-C method passing thing. And if you look closely, here you see something which resemble something like this. I called it index of or contains, but yeah, whatever. When this unlink function, if you look at the definition of the unlink function, it accepts a path, a system path, and then tries to delete it. So what happens is that my unlink function will try to see if that path is among this disallowed path, which I have already gotten like list of those paths, and see if it's part of that. And if it's part of that, then it will there's some code which is not properly reversed. Well, actually I have wait, I do have a reverse version in my blog post here, so you can see that here. Yeah, so it takes this path and tries to see if it's part of the disallowed path. So if it was part of the disallowed path, it will create an error and convince the application that you cannot access this path, so yeah, this device is not jailbroken. And if it was trying to access another path, a regular path, and then you say, yeah, cool, go on, you can do that, you know. So we call the original path. And how we did found these paths is because if you call the string function on this file here, if you just say string, okay, strings, it should be. If you call the strings function, you will not get all these paths that we have here. So it means that they're not just directly embedded there, and also not only with the strings command, but even with Ghidra, if you try to see in the data section and all, like basically search everything, you'll not find any of these paths. Why? If you click on this one, let's go to where this is. Yep, it's here. The data common. You see, it's been referenced in a bunch of places, cross references. I see it like 163 times, and basically it's null bytes, empty bytes, nothing there. But if you see, go to references and say references to this place, you'll see a lot of read operations, but there is at least a few write operations there. So that will be interesting, you know, because we do have a write operation to this place, at least two. And yeah, so if you click on the write operation to this place, and then let's see. So yeah, if you click there, and it will bring you to this function, and you can see the decompiled version of this function there above. And from what it seems, that this function does compute the strings dynamically, and then it stores it into that location of the disallowed path. But the problems here is that going through the logic of computing the strings and then running it will be a lot of energy, require a lot of energy and time. So basically we wouldn't want to waste all that time on that one. So we'll see what could be an easy way out of this problem. If you scroll down here, after computing all these strings, it does assign it to the disallowed path. And we see that assigning it does call the Objective-C method with some numbers, which in decimal is 414. Cool. So instead of computing all this, we can, with Frida, hook this function and then see the content of this computed string. So let's go to our Frida. I've already written this script which hooks the function, and then if this function is called and the number of the strings is less than 400, I'm going to just skip it, because well, already we said that it should be 400 from what we saw here. So let's let's do that. I switch it to the Corellium iOS device. Gonna launch it. Gonna either launch it the script, because I uploaded the script to the device. Guess we need to focus. Turn on the. Okay, should work now. It happens sometimes, so. Okay, there you go. There we have our strings listed. Just easy copy, and you can just copy it. You know, there are other ways we can write it to a file. We can write it to a file, and then there will be, of course, called other functions too. Basically, the fonts. If there are a lot of fonts in a device, you'll have the fonts too listed there, as you can see. So that's not what interested us. Of course, we'll have to rely on your intuition a lot to basically understand when is something happening. I'm gonna kill the app because I don't want it just keep running. Okay. So as you can see that these are the strings in the disallowed path symbol. Cool. So what's the vulnerability here? So if you think about it, how can it detect every location and how it should happen? You know, it says that if okay, for these sort of it's easy. For these sort of path, it will basically say exactly this path. But if there are paths which are not exact, like a full system file, maybe this sort of path that it does have, it would be hard, challenging for the tweak to really understand where it can hook the function or where it can prevent the file deletion or not. So we can exploit that. for our benefit. Not only that, we can detect a jailbreak because we will be able to detect the existence of this particular tweak by exploiting it. And the way we will do that, that we will run this code here that will get the home directory of the application. And since each application has a home directory, if I run it, and that application basically can create and delete any file it wants in the its home directory, in the documents or any other directory that is provided to it. So let's get the home directory of this particular application that we are testing. I guess we need to do something like this. Okay, so it's in the var mobile containers data application and this UID. So it ends with 112. If I go to files, so just want to be sure mobile. Applications, nope. Var containers data application, containers data applications, and 112. So it ends on 112 here. So let's go to the documents directory. We have already, for my previous test, delete this. We have no file here. So what we will do is we're going to create two files there from the command, one checktrain and one index.js. And we'll see. So at first, I'm going to comment out the code which deletes it. So just to see the files are really created. I'll copy this file code, paste it, come back, and indeed, two file has been created. Let's delete these files. And comment our code. So cool. From here we see that we cannot delete checktrain. Cannot delete it from the code because it's one of those strings which is part of computed string and then stored in the disallowed, and then in this logic of our part of this binary, it prevents from deleting those files. So not only we managed to detect that this device is indeed jailbroken, and not by accessing a part of the device that we cannot, but a part of the device that we do have access to it, because each application can indeed create files in its document directory, but we cannot delete it. And it says, oh, you don't have the permission to do that. So it's an easy way to detect this one. So we found the vulnerability and we did exploit it. I hope you liked it, enjoyed it. If you did so, please consider subscribing to the channel. We'll be releasing new videos on Frida and other related stuff. Yeah, see you, bye.